finish off our week before the break with a couple more example problems on two-dimensional collisions. In both cases here, we're going to see that these two-dimensional collisions or explosions have what we call, or what I call, funny angles in them, unlike the last example we did, which was a T-bone collision. You can see in this one, that we have a bundle of fireworks sitting on a table. It's exploding. All right, so it's an explosion. We've done explosions before. A bomb explodes into 2 or 3 pieces. We can handle that. This time, though, one mass or one piece of it goes directly north. One piece goes at 30 degrees south of east, and we want to know where the third piece goes. It's a little bit harder because of that funny angle in there. Let's draw a picture of it, though, to help us to visualize what's going on here. I'm going to put an X as my explosion point. This is where it is when it explodes. We have a piece that goes directly north at 120. I'm going to call that piece number 1. I'm going to make its mass 1.20 kilograms and its velocity 120 meters per second. Now the second piece is going to go south of east. This is south of east. "30 degrees south of east, the mass is 1.10 kilograms, and the velocity of this is 100 meters per second. Now, there is a third piece here. Firstly, what is the mass of the third piece? We're not told in this question directly, at least, what the mass of the third piece is, but we can figure that out. What is the mass of the third piece here? Logan? Good. 3 minus 1.2 minus 1.1, so that would be 0.70 kilograms. Mass of the third piece, 0.70 kilograms. Where do you think that third piece is going to go? Go ahead. Yep. Yeah, you know what? I think you're right. I think it's going to go south and west. I know it's going to go west because I have 0 initial X momentum before the explosion. I have to have 0 final X momentum after the explosion. If I have momentum to the east, then I have to have momentum to the west to cancel that. Now, as far as the up-down momentum goes, it's a bit of an educated guess on this one. Okay, I don't know for sure whether it's going to go west and up or west and down. I'm guessing that it's going west and down here. The reason I don't know whether it's going up or down is because before the collision, 0 Y momentum. Afterwards, 0 Y momentum. But I already have an up and a down component of the Y momentum. Depends on which one's bigger. If the Y component of this is bigger than this, okay, then object number 3's got to go upwards. If it's smaller, then it's going to go downwards. In the end, you must draw these black vectors correctly. This red vector, if you make a mistake on that or you guess wrong on that, that's not the end of the world. Okay, don't lose any sleep over that. Don't stress over where to draw that red vector. It's only there to help us visualize what's going on. If we draw it wrong, all right, it's a little bit harder to visualize what's going on, but it doesn't handicap us that much in solving this problem. All right. What do you see here that should raise a red flag? What do you see here that should bring to mind a key phrase that we've talked about? Yeah, exactly. We got 30 degrees funny angle, and we don't like funny angles. So we take it off to the side and we get rid of it so that we don't have to deal with it anymore. Okay, here's the 30-degree funny angle here. It's at 100 meters per second. I'm going to draw an X and a Y. And I'm going to solve for the value of X and Y so I don't have to deal with 100 meters per second anymore. Once I've gotten the X and the Y, the 100 meters per second is dead to us. We never want to deal with it again. We never want to see it again after we've got the X and Y component of it. So let's do that. Let's say cosine 30 degrees is equal to X over 100. That's adjacent over hypotenuse. Adjacent over hypotenuse. 86.6 meters per second. Let's say sine 30 degrees is equal to y over 100. That's opposite over hypotenuse. Now, I like to kind of square this off just so that I don't get it mixed up with my other stuff, but that's not a critical thing. Okay, that's just my little thing. One other thing that I like to do sometimes, and you can choose to do this or not. If it works for you, great. If it doesn't, that's okay too. Just drop your pens for a second and watch what I'm going to do here, okay? I like to erase this, and I like to draw in this. You see what I just did there? I replaced that 100 meters per second with 86.6 meters per second and 50 meters per second. And of course, the mass of it's still going to be 1.10 kilograms. Now we're going to break this into our X and Y components, just like we did that T-bone collision that we did a couple days ago. X component, Y component. We're going to say PI equals PF. Tell me, please, what the initial momentum of this bomb is before it explodes on the X component, the X axis here. 0. It's not moving, right? 0 on the X axis and the Y axis. There are 3 objects after the explosion takes place, so we're going to put in 3 terms, M1 V1F plus M2 V2F plus M3 V3F. Go ahead. Yep, you're right. Object number 1 has 0 momentum, so we could actually fill that in right now. Right, 0 X momentum because it's all Y. Right, 1.2 meters per second, but it's all on the vertical axis. Object number 2 has an X component. Object number 3, although we don't know what it is, also has an X component. So we're going to say 0 is equal to M2 is 1.10 kilograms. What's V2F here? What's V2F X component here? Reese, you get that one? Good. 86.6. Plus M3, which is, what is M3? Doesn't tell us, does it? Yeah. What did we find it was? 0.7, I think it was? 0.7 kilograms. 3 minus 1.2 minus 1.1. So we solve for V3F here. And when we do solve for V3F, we get negative 136.0857. So we said it was down and left. We were right about the left because we got a negative value for the X component, right? Now let's see if we were correct about the down. Let's do the Y component. PI equals PF. The initial momentum, once again, is 0 because the thing's at rest. M1 V1F plus M2 V2F plus M3 V3F. M1 is 1.2 V1F. Chase, what's V1F there? Good. Is it 120 or 1.2? I think it is 120. Yeah, it is 120. You're right. Thank you. Yeah, me too. That's exactly what I saw too. It is 120 meters per second. M2 is 1.10 kilograms. V2F. V2F. August, what's V2F for the Y component? Kristen, what's V2F for the Y component? 50, or we'll make it negative 50 because it's downwards. Does that make sense? M3 is 0.7. V3F Let's solve for V3F here. We get negative 127.1429. Guess what? When we said it was going left and down, we guessed correct. Okay, Joshua, I think that was you that said left and down, right? Yeah. We guessed, Joshua guessed correctly. Okay, we knew that it was going to go left. We didn't know for sure that it was going to go down. Now we do because we get a negative value for the y component. Yeah, go ahead. Yep.
The upper arrow is fully up, and
yep.
the side arrow
is only partially, yeah, partially down. But it depends on what the values are there. But that's why I thought you were right on that. It's because for that exact reason, yeah, because the one that was going upwards was all up, and the one that was going downwards was only partially down. Yeah, yeah, yep. All right, let's redraw this now, guys. We got negative 136. 136.0857. This is easy now, right? This is something we've done a million times here. We got negative 127.1429, and then our resultant vector, which is what we're looking for right here, is the hypotenuse, and then of course we can solve for theta as well. V is going to be the square root of 136 squared plus 127 squared. Theta is the inverse tan function of opposite 127 over 136. For V, I get 186 meters per second. How many digits should we be there? 3, yeah. 186 meters per second. And the angle for that one should be 43.1 degrees. And we're going to make that south of west. Or you could have gotten, what, 46.9 degrees west of south if you had to draw the vector diagram the other way around. I want you to look at this question for a second, and I want you to tell me what's different about this question versus those T-bone collisions at an intersection where a car is going north, a car is going to the west, and they collide and head off as one. Like, what's really the only significant difference with this question versus that question, Chase? Like what else? What other calculation? Good. Yeah, exactly. The only difference is that extra calculation that we have squared off in black over there, right? If you look at what we have down here in blue and what we have down here in green, it's exactly the same thing as you've been doing for a couple of days here now. Okay, over here in black, that's different. Okay, when we have a funny angle, we have to make it into one of the problems that we've already done. Okay, and that's what I've done over here by getting rid of that 100 meters per second, turning it into an 86 and a 50. I'd like you to take a look at a couple of questions on worksheet number 4 right now, just for a few minutes here. I'll have you work at your desks, and I'll take a walk around and see how you're doing. Then we'll do another example. The questions I want you to work on now are worksheet number 4, questions 4, 5, and 6. One more example that we want to do, the last thing that we want to do before the 1-week break that you guys have coming up next week. Example number 3. This one says a 19.5 kilogram red curling rock heading north at 4.5 collides off center with a blue curling rock at rest. Now that off center is kind of important here. If it collides directly on center, then one curling rock hitting another will just cause the second curling rock to bump straight up. But if it collides off center, then what we get is what we call a glancing collision, where they go off like this, right? And then we got funny angles. It goes from if it's on center, from a one-dimensional collision to if it's off center, a two-dimensional glancing funny angle collision. We want to know what the velocity of the blue curling rock is immediately after the collision. Let's draw this out here. We have a red curling rock that's going north at 4.5 meters per second. I'm not going to bother writing in the mass here because it's the same for each curling rock, okay? I'm just going to clutter the diagram up just a little bit less. If it was different masses, then I'd want to be sure to put that in there so I'd keep them straight. But since it's the same mass, if I happen to mix them up, red and blue, it doesn't really matter, right? Because it's the same thing. The blue curling rock is initially at rest. Now it says after the collision, the red curling rock goes at 30 degrees west of north. This is going to be object number 1, the red one, 30 degrees west of north. Okay, notice that it's drawn from the north axis, 30 degrees west from the north axis. And the velocity of that is 3 meters per second. Where do you think the blue one's going to go? We don't know the exact place, but we know the general vicinity, right? And we don't have to guess on this one. We know this one is going to go up and to the right. And we want to find its speed there. All right. So we know that this is a two-dimensional collision. We know that unless we're dealing with kinetic energy for some reason, we always have to do X and Y components here. But before we even go to the X and Y components, we got to get rid of that 30 degrees. I don't like funny angles. Get rid of the 30 degrees. So let's draw it over here. And let's label here an X and a Y. Let's find the value of X and Y here. Let's say, oh, this one's different. Usually X is cos and Y is sine. This time X is the opposite side. So we're going to say sine 30 degrees is equal to X over 3.0, or X is equal to 1.5 meters per second. Cosine 30 degrees is equal to adjacent, or the Y component, over 3.0, the hypotenuse. 3 cosine 30 is 2.5981. Now, square that off, or at least if you're like me, you square it off, just because, I don't know. Like, I guess maybe the main reason I do that, I square it off, is because that's what makes this question different than the T-bone collisions, right? And it helps me to see that's what makes it different. Otherwise, it's exactly the same as the T-bone collision. Let's erase this over here and replace it with 1.5 to the left and 2.5981 up. Now I don't have any funny angles other than object 2, which I don't worry about because that's what I'm solving for. X components, pi equals pf. Hey, what's the initial x momentum? Object number 2 is 0, right? What about object number 1? John, what's the initial x momentum of object number 1? Oh, the initial x momentum. Good. In other words, the total initial x momentum is 0, because number 1 is moving only on the y-axis and number 2 isn't moving at all. Afterwards, we've got m1 v1f plus m2 v2f. 0 is equal to, oh, this is nice. Anybody spot what I just spotted? Case? No, there's only 2 masses here. 2 curling rocks. What is it, Liam? Masses are the same, so they cancel. That doesn't happen to us all that often, but when it does, it's nice. Doesn't really make it any easier, really, but it's a little bit less work on a calculator and less chance of calculator entry error. V1F, X component, V1F. Rachel, what's the X component of V1F? Good, we're going to actually make it negative 1.5 because it's to the left, but yeah. And solve for V2F. V2F is just 1.5 meters per second. Let's do the Y component here now. This one's not quite so simple, but not too bad. We're going to say it's M1 V1I plus 0. There is a Y component to object number 1. There isn't to number 2. Equals M1 V1F plus M2 V2F. Once again, the same mass in each term cancels. V1I is 4.5 this time. V1F, Matt, Object number 1, final, y component. It's okay. Emma? Good. 2.598 is the final y component of object number 1. Is that okay? Plus V2F. So we solve for V2F here now, which is going to be 4.5 minus 2.598. 1.9019. Now it's easy, right? Now it's easy. Yep, go ahead, Chase. Yeah, actually it should be. Yeah. Yeah. The calculation that I did here actually used 2.5981. I just didn't write that down though. You're right. Thank you. All right. Now it's easy. Now we just say V2F is 1.5 to the right and 1.9019 this way. We solve for V using the Pythagorean theorem, and we solve for theta using the inverse tan function. I get V of 2 point, how many digits are we supposed to have for 2, I think, isn't it? Yeah. 2.4 meters per second. Theta is the inverse tan of 1.9 over 1.5. And we get 51 degrees, 52 degrees. And that would be north of east. It's at 38 degrees east of north. Good. What's different about this question versus the last one? Well, it's moving before the collision takes place. It's not an explosion, it's a collision. What's different about it versus the T-bone collision? Just this. That's it. Otherwise, it's exactly the same, right? So you got that stuff coming up starting Tuesday of the week back. That's kind of extra stuff, right? A lab due on Tuesday, an assignment due on Wednesday, and a unit test on Thursday. I am going to give you a bit of homework over the break. I'm sorry for that. Your homework over the break is going to be to finish off that worksheet up to number 8. Okay, up to number 8. And there is a practice question set I posted on Google Classroom about an hour ago as well that I'd like you to do and submit. Practice question set number 5. It's 3 or 4 questions. Can't remember. Combined, the homework probably shouldn't take you more than a half an hour, like your rule of thumb is. Okay, half an hour. Except that assignment due on Wednesday. That's going to be a little bit longer, right?